In the last video, we introduced the basic idea behind sliding window technique. We discussed a very simple problem where the window length was essentially constant. In this video, we'll discuss the case where window length isn't constant, which is the case for most medium to hard problems using sliding window technique. Let's first take a look at what does a variable window length really mean. In the last video, the window moved like this. As we can see, the window length remained constant. Under some given conditions, our window could potentially move like this. It first expands to length 4, then shrinks to length 2, moving forward, maintaining constant length, expands again to reach the end, after which it cannot move forward. As is visible, window length here isn't constant. One interesting thing to think about is what could be the worst case time complexity of such a window traversal. The worst case happens when we traverse in an alternating shrink-expand fashion like this. This is obviously assuming our rear and front pointer only move forward and never backward. Otherwise, we could get stuck and never really reach the end. Now let's take a look at the problem we'll be discussing in this video. Given an array of n positive integers and a positive integer s, find the minimal length of a contiguous subarray of which the sum is greater than or equal to s. If there isn't one, return 0 instead. This is very similar to the problem we solved in the previous video. The window size is not fixed here. In fact, we are supposed to find the minimal window size that satisfies the given constraints. The constraint being the window should have sum equal or greater than given value s. Let's try with a small example first. Here is an array of integers for the given value of n equal to 7 and s equal to 9. Just by looking at it, we can see the window 1, 3, 4, and 5 has sum 13, which is greater than s equal to 9. It is a potential solution. This is another window that sums to greater than or equal to s equal to 9 and of window length 3. Even better, here we have two windows which sum to s equal to 9 and are of length only 2. We can't do any better than 2 in this case. So this is our solution for the given array. The question is, how do we do this programmatically? As always, let's begin by coming up with a brute force solution. In the brute force solution, we go through all possible windows and try to find the one that satisfies the sum constraint and is also of minimal size. So if we know how to generate all possible subarrays, we are pretty much done, at least for the brute force solution. Now let's see how we can generate subarrays of an array. If you choose any 2 pointers on the array, you get a subarray. Mathematically this is NC2, but let's forget that. The way we can generate all possible subarrays is quite simple. We fix one of the pointers and consider all possible values of the other pointer. We begin with both pointers at 0, 0. Our subarray is element 1. We keep rear fixed at 0 and move front forward. We get the subarray 1, 3. We do this for all possible values of front, keeping our rear fixed. These are all the possible subarrays starting at rear equal to 0. Next, we start with rear at index 1. To keep duplicates out, we only move front in range starting at rear and forward. We repeat this until both rear and front are at the last index. We have now generated all possible subarrays of the array. With generation of subarrays out of the way, let's write our brute force code. We have a class minimum size subarray and 2 static methods, brute and optimize, defined on it. There are a bunch of assertion statements inside main which basically check the result returned by our methods. If we try to run this right now, we'll see our assertion statement, the very first assertion statement at line 24 fails. We declare our variables first. Min window will hold our final result. Front and rear are the pointers that define the ends of current subarray in consideration. We'll have 2 for loops. The outer one starts from 0 and goes till vector length. It marks the rear end of our current subarray. Local sum keeps the sum of current subarray under consideration. The inner loop starts at rear and goes till vector length and marks the front end of current subarray. Inside we add the element at front to local sum. If the local sum is greater than or equal to s, we update the value of min window, which holds our result, to be minimum of what we already have and the current subarray length. Finally, we return the result min window. If min window is equal to int max, it means we did not find a single subarray that satisfied our constraints, in which case we return 0. Let's think about the time complexity here. We have got two for loops. The outer one runs for n times. The inner one runs for n by 2 times on an average. Therefore, the overall time complexity of this solution is order of n square.
If we run the code now, we'll see the test cases are passing. Now let's take a look at an optimized approach. Whenever the problem talks about subarrays and some constraints over subarrays, you can think about applying sliding window technique. In this approach, we'll maintain a variable current window sum that will keep the sum of current window. Initially, both rear and front pointers are at index 0. The current window sum is 1 here. We expand our window by moving front forward. We go on expanding until the constraint of current window sum greater than or equal to s is satisfied. At this point, we have our first potential window that could be our solution. We maintain another variable min window length, which will be our solution. We update its value to be 4. Since we are interested in minimum possible window length, we try to shrink the window now and see if our constraints are still satisfied. We move rear forward. Current window sum now becomes 12, and we update min window length to be 3 because this is smaller than the last found value of 4. The constraint is still satisfied, so we try shrinking further. Here again, the window is satisfying our constraint, so we update the value of min window length to be 2. If we shrink further, the constraint is no longer satisfied here. We start expanding again until current window sum becomes equal or greater to s equal to 9. If we find a window that satisfies the constraint and also has window length lesser than the previous minimum, we update the value of min window length. We repeat this process until we can no longer move forward. Let's write some code now. We have already written our brute method. Now we'll be writing our optimized method. We have uncommented the assertion statements for optimized function. If we run it now, you can see the first assertion statement on line 41 is failing. We start by defining a few variables. Min window will hold our final result. We have rear and front and current window sum that will hold the sum of current window. We open a while loop that goes from front equal to 0 to front equal to nums array length. Inside, we update our current window sum by adding the element at front to it. This is the window expansion part. Now, if our constraint of current window sum greater than or equal to s is satisfied, we try to shrink the window until it is no longer satisfied. So we have another for loop that runs till current window sum is greater than or equal to s. Inside, we shrink the window by removing the element at rear from the current window sum and incrementing rear. Finally, we return min window. If we try running the program now, we can see all the test cases are passing. As for the time complexity of the solution, we are only visiting each element at most twice, so it's going to be linear time. That's it for this video. I'll catch you guys in the next one.